In this video, I'm going to go through OCR AS-level Chemistry, paper 2, and this is the this is paper 2, and this is the 2018 paper. I'm going to do the first half of the paper in this video and the second half in a later one. Okay, a student carries out a titration to determine the molar mass and structure of a weak acid A. Student follows the method below. Dissolves A in 100 centimeters cubed of distilled water and made the solution up to 250 in a beaker. So he's made a mistake there. He should have put it into a volumetric flask. And then the added solution, we're going to ask us about that, add the solution A to burette and did a titration against sodium hydroxide. What is meant by the term a standard solution? Well, that is just a solution that you know the concentration of to a high level of accuracy. And you usually use that solution in a titration. Sodium hydroxide is an alkali. What is meant by the term an alkali? Well, something that makes OH minus ions in solution. I'll probably say the best way of explaining that. Okay, so now this is about how to read a burette and stuff. So the student carried out a trial followed by 3 further titrations, and the diagrams below, right? So you've got to use this. So what's the initial reading here? So we should always record to nearest 0.05 centimeters. The initial reading for titration 1 is 0.45 centimeters cubed. It's halfway between 0.4 and 0.5. The final reading, I think that's 27.20. Titration 2, well, that starts off at 0.60 and finishes at 27.00. Titration 3, well, that's like half, what, 1 point, bit more than 2, bit less than 3, 1.25. And finally, that is going to be 27.75. Okay, so work out the titers there. By subtracting, we get 26.75, 26.4, and 26.50. Now, we want to work out the mean titer, so we only use the concordant values. They're within 0.1 of each other, so we only use those two. And 0.1, and the average of that obviously is 26.45 centimeters cubed. Right, uncertainties. The uncertainty in each burette reading is 0.05. So calculate the percentage uncertainty for titer in titration 1. Right, so we've got to multiply that by 2 because you take 2 burette readings, the initial and final. So that's 0.1 is twice that. And the titer was 26.75 multiplied by 100. That should give us 0.378%, so about 0.4%. Okay. The student realized that the solution of A had not been prepared correctly. How should the student, right, as I said earlier, says in there, he made it in a beaker. He shouldn't have used a beaker. He should have made it up in a volumetric flask. I think for 1 mark, that's all you need to say there. You don't have to sit around about making up to the mark and inverting and stuff. Just a 1 mark question. Right, now here's a different set of results. We're going to work out what is the molar mass of A and hopefully its structure. Okay, so let's just, the student prepared a solution. So he starts off with 250. This is a volumetric flask. And he added 1.513 grams. This is of A. He uses this to fill up the burette. So it doesn't go in the conical flask, it goes in the burette, that solution. And how much did he need? He needed a titer of 27.30 centimeters cubed of that. And he put this into, right, he had sodium hydroxide, 25 centimeters cubed of NaOH. And the concentration of that was 0.112 moles per decimeter cubed. Okay, calculate the molar mass of A. Right, well, how are we going to do that then? Well, we're going to find out the moles of sodium hydroxide, concentration times volume. Then they tell us that 1 mole of A reacts with, so we're going to halve it to get the moles of A. That will give us the moles of A in that much. Then we can work out the concentration of A, solution A. We can find out the number of moles in that solution. And then we can find out the MR because we know the moles and we know the mass of A. Okay, that's an overview of what we're going to do. Let's do it slowly. So moles of sodium hydroxide, moles NaOH, is equal to the concentration times by the volume. So that's going to be 0.112 multiplied by 25 over 1,000 dm cubed volume, of course. That is going to give us 2.8 times 10 to the minus 3 moles. That's how many moles we've got in the conical flask there. Right, how many moles of A is that going to react with? Well, we've got, it tells us here, 1 mole of A reacts with 2 of NaOH. So I'm going to write down the moles of A. That's going to be in this titer of 27.3. Is equal to a half times 2.8 times 10 to the minus 3. So that is going to be 1.4 times 10 to the minus 3 moles of A. So that's in that 27.3 centimeters cubed. So let's work that out. The concentration of A is equal to the moles over the volume. Well, it's in 250 centimeters cubed. That's 0.25 dm cubed. So it's 1.4 times 10 to the minus 3 divided by 0.25. Sorry, not talking about, not that at all. Divided by that volume, 27.3, so 27.30 over 1,000. Work that out, that gives us a concentration of 0.0513 moles per decimeter cubed. Now we need to find out how many moles we have got in this 250. So let's write that down. So moles of A in 250 centimeters cubed, that's equal to the concentration multiplied by the volume, which is 250. The concentration is this, 0.0513. The volume is 250. That's 0.25 dm cubed. So that is equal to 0.0128 moles. Okay, now we're in a position to work out the molar mass of A now, because we know here, we know that the moles, well, let's write the equation down. Moles is equal to mass over MR. We want to find out the molar mass, the MR, so MR is equal to the mass divided by the moles. Right, the mass, they tell us, is this, 1.153 grams. And then the moles we've worked out is this, 0.0128. And if you work that out, that gives you 117.97. Okay, that to 3 significant figures is 118. So that's 118. I think it does ask us to give it to appropriate number of significant figures. If I just scroll up. No, give your answer to the nearest whole number. So it's 118 is the answer. Yeah. Right, now the next part of this question. A is an organic acid containing carbon, hydrogen, and oxygen only. And one molecule of A contains 2 carboxylic acid groups there. Suggest the structure of A. Right. We're going to have 2 carboxylic acids. Now they can only go on the ends, can't they? So I'm going to put this. We don't know what's in the middle there, but they've got to go on the ends. You can't have. It's got to go on the end of a carbon chain. Right. Each one of those is going to weigh. Well, carbon is 12. The oxygens are 16. So that each one of them is going to be 45. Okay. So that means this bit in the middle. Well, the whole thing weighs 118. Minus 2 times 45 is 90. So that bit in the middle has got, that's 28. So all this bit here has got to be 28. Now what could that be? It's only got carbons and hydrogens. So I think it's pretty obvious that that is 2 CH2 groups. So that's 14 for that one, 14 for that. Okay, so that's what it is. Butane dioic acid. That is the most likely structure of A. Okay, sodium sulfide is an ionic compound of sodium and sulfur. Draw a dot cross diagram to show the bonding in sodium sulfide. Right. Okay, so sodium is 1s2, 2s2, 2p6, 3s1. So it's going to lose that 3s electron to form an Na single charge. Okay, so there's going to be no electrons in the outer shell. So I'll just draw sodium like that. Sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. So that's going to gain 2 electrons to make that 2p6, form an s2 minus ion. So it's going to get 8 electrons in its outer shell. So I'll draw that like this. Here's a sulfur. It's got 6 of its own electrons, the crosses. And it's got the 2 extra ones it's got from sodium, the dots. And I'll put a charge on that of 2 minus. Okay, so that is the dot cross diagram. Okay. The table below compares the properties of sodium sulfide and sodium and sulfur. Let's complete this table. Okay. Now, we've got to think, all right, sodium sulfide, it's ionic, okay? Na plus, 2 Na plus ions and 2 sulfide ions. So it is going to be giant ionic lattice. It's giant. It won't conduct when it's solid, poor, because the ions can't move. But then when it's liquid, it will conduct well, because the ions can move and carry the current. The sodium ions and the sulfide ions can move. Sodium, well, that's just sodium metal, so that is a metallic lattice, so that's going to be giant as well. Can it conduct when it's solid? Yes, it can, because it's got delocalized electrons. And it can also conduct when it's liquid. It's still got delocalized electrons to carry the current. And sulfur, right now, sulfur exists as S8 molecules. So it's small molecules, so it's simple. And it can't conduct when it's solid or liquid. Poor conductor, because it's got no delocalized electrons and it's got no free ions. And there's no ions in it that can move about. Okay, so that's a fairly straightforward table. Right, selenium is in the same group as okay, so here's selenium down here. And we've got to write down the electronic structure. Okay, so we've got 1s2 is obviously filled up. See, lads. Okay, and then we've got 2s2, which is here. 2s2, so that's filled up. And then we've got 2p6, that's filled up. And then we've got 3s2 filled up. 3p is completely filled. 3p6. 4s2, beginning to run out of colors, is filled up. 3d is completely filled. I'll do a different color. 3d, got 10 electrons in there. And then finally, we've got 4p6, and we've got 1, 2, 3, 4. So that's 4p6. That's electronic configuration of selenium. Okay, sodium selenide. Now that's going to probably have this formula, Na2S, because it's going to form Se, sorry. It's going to form a 2- ion like oxygen in the same group and like sulfur in the same group. That reacts with hydrochloric acid to form a toxic gas B with a relative molecular mass of 81. Now look at the MR of selenium there. It's a bit odd because I've written over, but it's actually the atomic mass of selenium is 79. So probably this toxic gas of 81 is H2SE, which would, like, you get H2O, H2S. So it's analogous to that. It's a gas though. Right, and I didn't know that was poisonous, but apparently it is poisonous, but that's a sensible suggestion. Right, so we're going to have Na2Se. It's going to react with water to form, hydrochloric acid, not water. Right, we're going to form H2Se, that's the poisonous gas. And we need 2 of those. What's going to be left over? It's obviously going to be 2 sodium chlorides. There we go. It's actually an acid-base reaction. I think this Se is behaving as a base, accepting H+ ions from the hydrochloric acid. We don't need to say that though. Right. The question is about halogens. Bromine is used to extract iodine from a solution containing iodide ions. Write an ionic equation for this reaction. Okay, so there's a halogen displacement, isn't it? So we're going to get Br- ions in solution, Br2, and we're going to react that with I-. What's going to happen is the bromine is going to oxidize the ion, it's going to iodide, it's going to remove an electron from it, so you're going to get I2, so we need to do that, and you're going to get 2 electrons sticking onto the bromine, so 2Br-. Right, so that's one. Explain. So there's 4 marks for the whole thing. Why is iodine less reactive than bromine? Right, what do we need to do? So probably 3 marks for this. Right, when they both react, they both accept electrons into the outer shell. Okay, easier for bromine to accept electrons because the shell that they go into is closer to the nucleus, and so you've got more stronger attraction by the nucleus. Okay, iodine can be used for small-scale purification of drinking water. Iodine reaction shown below. Using oxidation number, explain why this is disproportionation. Okay, so oxidation numbers in iodine is 0 because it's the uncombined element. Now the oxidation number of iodine in Hi, well, that's got to be -1 because don't forget hydrogen has always got an oxidation number of +1 in its compounds. And then what's the oxidation number of iodine in HiO? Well, I always use the sum of the oxidation numbers is equal to the charge on the species. Well, the charge on Hi is 0. Hydrogen is always +1. Iodine, we don't know. Let's call that I. And oxygen is always -2. So just rearrange that. We get I -1 is equal to 0. So iodine has got an oxidation number of +1 there. So it's -1 there, and it's +1 here. Now, when the oxidation number goes down, the element has become reduced. And when the oxidation number goes up, as for this one, it has become oxidized. So the iodine has become simultaneously oxidized and reduced. So that is what disproportionation is. Okay, chlorine is used to purify water on a large scale. State one disadvantage of using chlorine for purification of drinking water. Chlorine gas is toxic, and so it's got to be handled pretty carefully. It may not be that may be inconvenient and costly. Okay, right. Right, we've got a bond energy calculation now. Hydrogen reacts with chlorine to form hydrogen chloride, as shown in that equation. You've got the bond enthalpies there. Calculate the bond enthalpies for the HCl bond from the information above. Right, so we know what the enthalpy change for this reaction is. That's minus 184 kilojoules per mole. Right, what I like to do with these bonds, if you're given bond energies, is to draw one arrow going down. I'm going to break every bond and get gaseous atoms. So we're going to get 2 hydrogen atoms and 2 chlorine atoms. And then we're going to build it all back up again by forming bonds. Okay, so you've got a Hess's law cycle here. Right, let's look at the red arrow. What we're doing, we're breaking bonds. Breaking bonds, of course, is endothermic, so that's going to be positive values. We're breaking one of those, so that's plus 436. And we're breaking a chlorine-chlorine bond, that's plus 243. Add that up, you get plus 679. And what we're doing on this green arrow, well, we're forming 2 bonds of HCl. So let's call that bond, let's call the bond energy of that, let's call that X. It's going to be 2x, but it's going to be minus 2x because we're forming those bonds, so it's exothermic, so it's a negative value. Right, now all we've got to do is put those in. So we know that minus 184 by Hess's law, so that is equal to this red number here, plus 679, and plus minus 2x. So let's do that, rearrange it. We get minus 2x is going to be equal to minus 863. So 2x is equal to 863 plus 863. So x is equal to 431.5 kilojoules per mole. That is the strength of our HCl bond. That's the bond energy plus 431.5 kilojoules per mole. So I like to do it using a Hess's law cycle. Surely working out there, because if you make a little mistake and you don't get the right answer, you'll get no marks. Okay. Enthalpy of vaporization is the enthalpy change when 1 mole of a substance changes from liquid to gas. Okay, so write an equation to represent the enthalpy change of vaporization of bromine. Well, bromine is Br2. Okay, so we've got Br2, and it goes from a liquid, so it's liquid, and it goes to Br2 gas. That's what we've got to do. Suggest whether it's going to be exothermic or endothermic. It's obviously going to be endothermic. Why is it going to be endothermic? It's because you're having to break intermolecular forces. In this case, these forces are dispersion forces, and it requires energy to break them to separate the molecules so they're in the gaseous phase. Okay. The reaction of ammonia with oxygen to form nitrogen monoxide. Okay, they give you the equilibrium reaction below. It's minus 905 kilojoules per mole. The Ford reaction, okay, converts NH3 to NO. Complete the enthalpy profile for this diagram for this reaction. We've got to label EA, and we've got to label delta H. And okay, so what we're going to do is we want energy. On this axis. And this is the progress of the reaction, time, something like that, on that scale. Now this is an exothermic reaction, so that means there is more energy, more chemical energy in the products than in the reactants. So I'm going to draw my, more energy, chemical energy in the reactants. So the reactants are going to be up there. So it's going to be 4 ammonia plus 5 O2. And we've lost 905 kilojoules of chemical energy as thermal energy. So that's going to be lower down here, the products. And that's 4NO plus 6H2O. We need to put in, okay, what happens during the course of the reaction. There is it has to go to higher chemical energy first before you get any released. And that's the activation energy, that bit. So we've got to label the activation energy. So activation energy is that bit from there down to there. And the enthalpy change of the reaction is from the reactants down to the products. It's there. Minus 905 kilojoules. Okay, so that's it. That's the diagram. Right. I'll make that a bit bigger. 5.10 tons of NH3 are converted to NO. Calculate the energy released in kilojoules for this conversion. Now, I'm going to just paste that. Then we need this equation. I'm going to copy it. Right, like that. Just paste that equation in, and this is quite important because we'll see here, look, it says, right, that equation, you get 905 kilojoules per mole out when you react 4 moles, when you turn 4 moles of NH3 into 4 moles of NO. Okay, so that means we have to work it out for 1, so therefore for 1 mole, it's going to be 905 divided by 4. That's equal to 226.25. That's for 1 mole of ammonia. Now we have 225, sorry. Now the next thing we have to do is work out how many moles of ammonia we actually have in this 5.1 tons, okay? So we need to know 5.1 tons that is equal to 5.1 times 1,000 kilograms. And then we need to convert that into grams. How many grams have we got in a kilogram? It's 1,000, so that's equal to 5.1 times 10 to the 3 times 10 to the 3 grams. Of course, that's equal to 5.1 times 10 to the 6 grams. Now let's work out the number of moles of ammonia. So moles NH3 is equal to mass over MR. Okay, the mass we have got is 5.1 times 10 to the 6 divided by the MR of ammonia, which is 17 molar mass of ammonia. That gives us a total number of moles of, that works out is exactly 3.0 times 10 to the 5 moles, okay. Now for 1 mole we get that much energy out, so what's the total amount of energy we get out for all of this altogether? So energy out is equal to the quantity per mole multiplied by the number of moles. The quantity per mole is 226.25 multiplied by the number of moles, 3 times 10 to the 5. And that gives us a final answer of, not quite final, but nearly, 6. So we should turn a calculator. That gives us a total of 6.7 0.875 times 10 to the 6 kilojoules. Okay, to appropriate number of significant figures, we should give it to 3 significant figures because that's the 3 sig figs and that's the 3 sig figs, the mass. Okay, so it's 3 significant figures. That is, we'll leave it in standard form, obviously. 6.79 times 10 to the 6 kilojoules. Okay. All right. Write an expression for the equilibrium constant in this reaction then. Okay, so what's that going to be? It's going to be the products on the top. So it's going to be H2O concentration of to the power of 6 multiplied by the concentration of NO to the power of 4 divided by the concentration of ammonia to the power of 4 multiplied by the concentration of oxygen to the power of 5. Okay, predict the conditions of temperature and pressure for maximum equilibrium yield. Explain in terms of Le Chatelier's principle, and then say why we might not actually do that. Okay, what we need to think about that. Okay, so this is a fairly standard, straightforward question. Okay, let's think about temperature first of all. Right, what kind of a temperature do we want? Well, the reaction is exothermic. So Le Chatelier tells us, Le Chatelier's principle tells us, if we lower the temperature, the reaction will tries to increase the temperature by moving in the exo direction. In the exothermic direction, i.e. forwards. So we'll get better yield at a lower temperature. Now, why might not that be done at a low temperature? Well, this is because it's between a rate and other rate we're talking about here. Probably it's done at a high temperature, not a really low temperature, because a low temperature, the rate of reaction will be too slow. So it may be, yeah, you get a very good yield of NO at equilibrium, but you'd have to wait an awful long time for it to reach equilibrium, forever. Okay, so that's why the temperature might not be too low. Now let's think about the pressure. Before I scroll down, let's just count up the gas molecules and stuff. So we've got a total of 5. We've got 9 gas molecules on the left, and we've got 10 gas molecules on the right. So the gas molecules, gas moles, increases right to left. So Le Chatelier tells us if we drop the pressure, the equilibrium will try and raise the pressure by moving towards the higher number of gas moles. Okay, so in other words, low pressure, we'll get a better yield. However, it might not be done at a low pressure, because at low pressure, the concentration of the gas molecules is low, and the rate of reaction may be too low. Okay, now they did say other operational factors, and they're usually talking about cost there. Well, having low pressure usually makes it cheaper, and having low temperature usually makes it cheaper. So you wouldn't, they give you the good yield, but obviously might not be able to. So you wouldn't you wouldn't change those conditions on a basis of cost. It's the rate here which is the important thing. Both of them. To give you a good yield is going to give you a low rate, so you might not actually use the prediction that we put there. Okay, next question then. Now, I think that is as far as I'm going to go. That's about halfway through the paper, so I'm going to continue with that in the next video.